Okay, so now we want to talk about a forced mass spring. So the first thing is if it has no damping at all, if B is equal to 0, so B is the damping coefficient, K is the spring constant of 2, mass is a half. But if we start this system, if we pull the spring or push it down or pull it down and let go, there is no force, and we just get a simple harmonic motion back and forth. Now, the forcing function in this case is F cosine omega t. So if I set F equal to 1, I guess 2, it doesn't really matter, the constant just gives us more force. But if we let omega equal 1, that means that the natural frequency, so in this case K is equal to 2 and M is a half, the natural frequency is 1 over pi. The forcing frequency comes from cosine of t, so the forcing frequency would be 1 over 2 pi. So in this case, the natural frequency is 1 over pi, and the forcing frequency is 1/2 of that. So if we start this at 0, 0, so we can start at 0, 0 because we have an external force, and you'll see the external force working up here. If I start this as close to 0, 0, what I get, and again it's kind of hard to tell what's happening with respect to beats and so on, but if you notice the force is pushing down at a frequency of 1/2 or 1 over 2 pi, or 1/2 of 1 over pi, and then the natural frequency of the spring is 1 over pi. You see sometimes the force is working against the spring and sometimes it's working with the spring. So if it works to push the spring in the same direction it wants to go, we're going to get a displacement that's larger. If it's working against the spring, we're going to get a displacement that's smaller. That's why you get these different peaks and valleys here. So let's change the forcing frequency to something a little closer to the natural frequency. So if I change this to 1.5 or 1.5 or close to it, now if we start this again 0, 0, we start seeing this idea of beats. Is that now the forcing frequency is 3/4 of the natural frequency. So it's not quite the same, but it's closer. So that just means that for a longer period of time, the spring and the force kind of work together to produce a larger amplitude in a longer period of time. So the period of the beats basically goes, it's kind of hard to draw this, but the period of the beats and the amplitude are affected by that. So if we keep increasing that towards 2, maybe get a little closer here and start this, we should see, and again the graph is adjusted here, you'll notice the amplitude, but it takes longer. The spring and the mass are kind of working together for a longer period of time and against each other for a longer period of time, but it just oscillates back and forth, increasing the amplitude and increasing the period. So the beats are going to be these kind of long curves that are outlining the rapid oscillations. All right, so if we get closer to 2, even 1.9 or something, we're going to see that again the amplitude changed all the way up to 20. It's taking a long time to get to a period. This is actually right now would be about half the period of the beats. It's kind of hard to see the whole thing on this graph, but again you'd notice that the spring and the force work together for a longer period of time and then work against each other for a longer period of time. So it takes it a while to kind of get going, but then once it gets going, it gets to a point where it starts working against each other and slowing down. All right, so the last thing we'll look at is when we have resonance. And resonance happens when the frequency of the force is the same as the frequency of the or the natural frequency of the spring. So here K with M equaling a half, K equaling a 2, the 2 gives us the natural frequency of 1 over pi, and if omega is 2, then the frequency of cosine of 2t would be 1 over pi. So what happens here is we should see resonance. And let me just start this again at 0, 0. And you'll notice that the force and the spring are working in tandem. So there's never a time that they're out of sync or they're working against each other. It just keeps going crazy. It's getting as high as it can. But I kind of think of this as pushing a kid on a swing. If you push at exactly the right time, the child or the kid just keeps getting higher each time, and that's what you want to do, is to maximize that point at which you, or that time and that point at which you push that child. So this is the same thing. The external force is working exactly in tandem with the spring, and it creates a resonance. So the amplitude just continues without bound, and the period is infinite. So again, if we just watch this, we can adjust the forcing frequency to approach the natural frequency, and the closer they get together, the longer and the more amplitude of the beats we have. And once we get the resonance where the natural frequency and the forcing frequency are the same, we get an increase without bound of the amplitude. All right.